Tonight, we are going to talk about something that sounds like science fiction, but is sitting in your hand right now. You have heard the word before, quantum. It gets used to sell almost anything. Quantum computing, quantum healing, quantum leap. Most of the time the word means nothing at all. But underneath all of that noise, there is a real thing, a real theory, and it is the single most successful idea in the history of science. Here is what almost no one tells you about it. Quantum mechanics has never once been wrong. In 100 years of testing, in every experiment ever devised to try to break it, it has passed. It predicts the behavior of matter to a precision so fine, it is like measuring the distance from here to the moon and being accurate to the width of a single human hair. It built the modern world. The screen you may be looking at right now, the chip inside your phone, the laser in a checkout scanner, the light from an ordinary bulb, none of it works without quantum mechanics. It is, by any measure we have, the most thoroughly proven description of reality we have ever written down. And it says that reality, underneath, does not behave the way you think it does. It says that a particle can be in two places at once. It says that nothing is truly decided until it is measured. It says that two objects can be tied together across the whole width of the galaxy, so that touching one instantly answers for the other, with nothing passing between them at all. It works perfectly, and it makes no sense. That is not a contradiction I am inventing for the sake of a story. It is the honest situation, and it has been for 100 years. We have a theory that gives the right answer every single time, and we still cannot agree on what it is telling us about the world. And here is the part that makes this more than just a curiosity. The man who helped build this theory, the man who handed us one of its very first pieces, spent the rest of his life insisting that it could not be the truth. He never denied that the mathematics worked. He admitted that openly. What he refused to accept was what the mathematics seemed to be saying about reality, that the universe is, at its root, uncertain, that it deals in chance, that there is no quiet, solid, definite world sitting underneath, waiting to be uncovered. His name was Albert Einstein, and he was wrong. That sentence is harder to say than it sounds, because Einstein was rarely wrong about anything. But on this, the deepest question of his life, the question he wrestled with for 30 years and carried unresolved to his grave, the universe turned out to disagree with him. And we did not find that out until long after he had died, in an experiment so strange and so precise that it took us decades even to figure out how to perform it. By the end of tonight, you are going to understand that experiment. You are going to understand what Einstein could not accept and why, and exactly how the universe answered him. You are going to understand the most famous thought experiment in all of physics, the one with the cat that is somehow both alive and dead. And you are going to understand why a theory that powers every device you own is still, at its very center, one of the great unsolved mysteries of human knowledge. Before we begin, if you find this kind of slow, deep exploration calming, a quiet like or subscribe really does help the channel grow. It makes a real difference. Now, let us begin. So, settle in, let the lights go low, let your shoulders come down away from your ears. We are going to start, as these things always start, with a single small problem that no one thought was important. A tiny crack in a picture that everyone believed was nearly finished, and we are going to follow that crack, patiently, all the way down into the foundations of reality while you drift off to sleep. To understand how strange this gets, you have to first understand how certain everyone was just before it all came apart. Picture the world of physics in the final years of the 19th century. It was a confident place, For more than 200 years, the rules laid down by Isaac Newton had worked without fail. You could use them to predict the motion of the planets, the path of a cannonball, the swing of a pendulum, the turning of the tides. The heavens and the earth ran on the same clean machinery, and that machinery could be written down in a handful of equations. And it was not only motion. By the late 1800s, the other great mystery, the mystery of electricity and magnetism and light, had been gathered up too, folded into a beautiful set of equations by a Scottish physicist named James Clerk Maxwell. Light, it turned out, was a wave, a ripple traveling through the electric and magnetic fields that fill all of space. That was settled. That was known. So by the year 1900, many of the most respected scientists alive believed the work was very nearly done. There is a story, often repeated, of a famous physicist telling his students that the great discoveries had all been made and that the future of the field lay only in measuring the known quantities to a few more decimal places. Whether he ever said those exact words is uncertain, but the feeling behind them was real and widespread. The building was finished. There were only a few small details left to tidy up around the edges, and there were a few small details. There always are. 2 or 3 little measurements that the great theories could not quite explain. Nothing serious, nothing anyone lost sleep over. Loose threads hanging from the corner of a finished tapestry. But you have to be careful with loose threads, because when you pull on the right one, the whole tapestry can come undone. One of those threads had to do with something so ordinary that you have seen it 1,000 times without thinking about it. The color of heat. Think about a piece of metal. An iron bar, say, held in a fire. When it is cool, it is dark. As it warms, it begins to glow. First, a dull red. Then, as it grows hotter, a brighter orange. Hotter still, and it turns yellow, then white. And at the very highest temperatures, it edges toward a pale blue. You have seen this. The coils of an electric stove, the filament of an old bulb, the embers in a fireplace shifting from red to orange as they catch. The color of a hot object tells you its temperature. This is so reliable that astronomers use it to measure the heat of distant stars. A red star is cooler. A blue-white star is fiercely hot. This seems simple. But in the 1890s, when physicists tried to use their finished, confident theories to explain exactly why a hot object glows the colors it does, the mathematics broke. The theory, they had said something absurd. It predicted that any warm object, a stove coil, an iron bar, your own body, should be pouring out a vast and endless flood of high-energy light. Not just the gentle warmth and visible glow that real objects give off, but an unstoppable torrent of ultraviolet and beyond, growing stronger and stronger without limit at the shorter wavelengths. By the equations of the time, every warm thing in the universe should be blasting out infinite energy. This was so obviously, ridiculously false that it later earned a dramatic name: the ultraviolet catastrophe. Because if it were true, simply sitting near a warm fireplace would bathe you in lethal radiation. The universe would be a deadly place, and it plainly is not. You can sit by a fire and feel only its gentle warmth. The catastrophe never happens. So the theory was wrong. Not a little wrong, catastrophically wrong, in the literal sense. And no one could see why. The equations that worked so beautifully everywhere else, that described light as a smooth, continuous wave, gave a monstrous and impossible answer for the simplest thing imaginable: the glow of a warm object. This was the loose thread, and the man who reached out and pulled it did not want to. He did not set out to overturn physics. He was a careful, conservative, deeply traditional man, and what he found would trouble him for the rest of his life. His name was Max Planck. In the year 1900, Planck was in his early 40s, a respected professor in Berlin, exactly the sort of person who believed in the finished, orderly world of classical physics. He had spent years on this problem of the glowing heat, and he was stuck like everyone else. The honest equations gave the impossible answer. So at last, almost in frustration, he tried something he did not believe in. He tried a trick. He asked himself, what would happen if energy did not flow smoothly? If, instead of pouring out in a continuous stream like water from a tap, the energy of light could only come in small, separate, indivisible amounts, little packets, lumps, as though the warm object could not give off just any amount of energy it liked, but had to hand it over in whole units, one packet at a time, with nothing in between. He called these packets quanta, from the Latin word for how much. A quantum of energy, the smallest amount that could be given. It is worth slowing down on how strange this idea is, because it is the seed of everything that follows tonight. We do not normally think of energy as coming in lumps. Pour yourself a glass of water and you can fill it to any level you like. A drop more, a drop less, any amount at all, smoothly, continuously. That is how everyone assumed energy worked too. Any amount, smoothly, with no smallest step. Planck was suggesting something different. He was suggesting that at the level of light, the universe does not work like pouring water. It works like counting coins. You can have 1 coin, or 2 coins, or 3. You cannot have 1.5 coins. There is a smallest unit, and everything comes in whole multiples of it. And here is the thing that haunted him. When he put this strange rule into his equations, when he insisted that energy could only come in these small whole packets, the impossible answer vanished. The ultraviolet catastrophe disappeared. The equations now predicted exactly, perfectly, the real colors of a glowing object at every temperature, with no flaw anywhere. The numbers matched reality to the last decimal place. It worked. It worked completely. And Planck did not believe it. This is one of the quiet, human truths at the start of this whole story, and it is worth sitting with for a moment in the dark. Max Planck did not think he had discovered something true about the universe. He thought he had found a mathematical trick, a bookkeeping device, a strange assumption that happened for reasons he could not explain to give the right answer. He fully expected that someone would come along soon and show how the packets of energy were not real, how they were just a clever shortcut to a result that could be reached some more sensible way. He spent years afterward trying to make the strangeness go away, trying to fold his discovery back into the smooth, continuous, comfortable physics he had grown up with. He never managed it. No one ever has, because the packets were real. Planck had not found a trick. He had found a crack in the floor of the world, and through that crack, whether he wanted to or not, he had caught the first glimpse of the layer beneath. A layer where the universe is not smooth and continuous, but grainy and lumpy, and built out of indivisible smallest pieces. He had, almost against his will, started the revolution. And the date is worth remembering, because in a sense, it is the birthday of everything we will talk about tonight. The 14th of December, in the year 1900, the day Max Planck presented his packets of energy to the world and quietly, without meaning to, ended the old certainty forever. But a crack is only a crack. One strange assumption buried in one difficult problem about glowing heat was not enough to bring down the finished building of classical physics. Most physicists, if they noticed Planck's work at all, assumed exactly what Planck himself assumed, that it was a curiosity, a temporary patch, a bit of mathematical strangeness that would be tidied away in time. It took someone else, someone younger and far less cautious, to look at Planck's reluctant little packets and say a dangerous thing, to say, what if they are not a trick at all? What if they are real? What if light itself is made of them? And the person who said it was a 26-year-old patent clerk working in an office in Switzerland, who in that very same stretch of years was about to change physics more than anyone since Newton. A young man named Albert Einstein, which means we have arrived, already, at one of the strange and beautiful ironies at the heart of this whole story. The theory we are following tonight, the theory of the uncertain, the unsettled, the indefinite universe, the theory that Einstein would spend the last 30 years of his life resisting with everything he had, is a theory he himself helped to build. He did not stand outside it and reject it. He reached into its foundations and laid one of the first stones. And only later, once he saw the full shape of the thing he had helped begin, did he turn against it. To understand how that happened, we have to follow him into the patent office and into the second of the small loose threads, the one about light-striking metal that he was about to pull. In the year 1905, Albert Einstein was 26 years old, and he was not a professor. He did not work at a university. He had struggled to find an academic post at all, and so he had taken a steady job as a clerk in the patent office in the Swiss city of Bern, examining other people's inventions during the day. Physics was what he did in the gaps, on scraps of paper at his desk, on the walk to work, in the evenings. And in that single year, that one extraordinary year, this unknown clerk published a small number of papers that would each on its own have secured his place in history. One of them explained the jittering dance of tiny particles suspended in water, and in doing so proved, finally and beyond argument, that atoms are real. Two of them laid out his theory of special relativity, the work that would eventually make him the most famous scientist who ever lived, and which we spent another long night exploring not so long ago. But the paper that mattered most to the story we're telling tonight was none of those. It was a paper about light-striking metal, and it was the only one of his 1905 papers that Einstein himself described as truly revolutionary. Here was the puzzle. Another of those small, nagging loose threads. When you shine light onto certain metals, the metal can give off a faint electric current. The light knocks tiny particles, electrons, loose from the surface, and they fly off. This was known. It is called the photoelectric effect. It sounds obscure, but hold on, because the way it misbehaves is the whole point. If light was simply a smooth, continuous wave, as everyone believed, as Maxwell's beautiful equations insisted, then this effect should follow a very particular set of rules. A brighter light carries more energy. So a brighter light should knock the electrons loose more forcefully, sending them flying off faster. And a dim light should still work, given enough time, slowly delivering its energy until at last an electron shakes free. That is what a wave should do. That is what everyone expected. But that is not what happens. What actually happens is strange in a way that broke the rules. It turns out that the color of the light matters more than its brightness. Shine a red light on the metal, and no matter how bright you make it, no matter how powerful, not a single electron comes loose. You can pour red light onto the surface all day long, blindingly bright, and nothing happens at all. But switch to blue light, or to ultraviolet, even a faint and feeble amount of it, and electrons immediately come flying off. This made no sense in the world of waves. Brightness is the strength of the wave. A bright red light should carry far more energy than a dim blue one. Why should the dim blue light succeed where the powerful red light completely fails? Why should the color and not the strength be the thing that decides whether anything happens at all? Einstein saw the answer. And the answer was to take Max Planck's reluctant little packets, the ones Planck himself thought were only a mathematical trick, and to say the dangerous thing out loud. To say that they are real. That light is not a smooth, continuous wave after all, or at least, not only that. That light actually arrives in tiny, indivisible packets of energy, lumps, grains. We now call them photons, particles of light. And once you picture light that way, as a hail of tiny separate packets, the whole puzzle dissolves and falls into place. Here is the picture. Imagine each electron in the metal is held down, fixed in place, and to knock it loose, you have to hit it hard enough in a single blow. Now, the energy carried by each individual packet of light depends not on how bright the light is, but on its color. This is the key. A packet of red light is a low-energy packet. A packet of blue light carries more energy. A packet of ultraviolet, more still. The color of light is the energy of its individual packets. So now think about what happens. A red packet strikes an electron. It is a weak blow. It does not carry enough energy in that single hit to knock the electron loose. And making the light brighter does not help at all, because a brighter red light just means more weak packets arriving, more feeble blows, each one still too weak on its own. 1,000 gentle taps will not do what one firm strike can do. The electron never comes free. But a single packet of blue light strikes with enough energy in that one blow to knock the electron loose at once. So even a dim blue light, just a few packets, frees some electrons immediately. The brightness only controls how many packets arrive, and so how many electrons come loose. But the color, the energy of each single packet, decides whether even one of them can come loose at all. It fit perfectly. Every strange feature of the photoelectric effect, every rule that made no sense for a wave, made complete and total sense the moment you treated light as a stream of particles. Einstein had taken Planck's bookkeeping trick and turned it into a statement about the actual nature of light. Light, he was saying, is grainy. It comes in pieces. And this was, frankly, almost too much for physicists to accept, because the wave theory of light was not some shaky guess. It was one of the great triumphs of the century. There was overwhelming, beautiful, decades-old evidence that light is a wave. Light bends around corners the way waves do. Light spreads and overlaps and forms ripple patterns the way waves do. You could not simply throw all of that away and declare light to be particles. But you could not argue with the photoelectric effect either. The experiments were clear. Einstein's particle picture got every detail right. So, which was it? Was light a wave, or was it a particle? And here we arrive at the first of the deep and genuine strangenesses at the heart of this whole subject, the strangeness that we will spend the rest of the night sinking into. Because the answer, the real answer, the one the universe gives, is not one or the other. The answer is both, and neither. Light behaves like a wave in some experiments and like a particle in others, and there is no single familiar picture, nothing from the ordinary world of your experience, that captures both at once. Light is something for which we simply do not have a word, because there is nothing else like it. We call it a wave when it acts like a wave, and a particle when it acts like a particle, and we admit, quietly, that it is really neither of those things, but some third thing that our minds, built for a world of rivers and pebbles, were never shaped to hold. This idea would soon grow far stranger still, because within 20 years, a young French physicist named Louis de Broglie would ask the obvious, vertiginous next question. If light, which everyone had always thought was a wave, can also behave like a particle, then what about matter? What about the things everyone had always thought were particles? The electrons, the atoms, the solid stuff of the world. Could they too sometimes behave like waves? The answer, impossibly, turned out to be yes. Matter, the electrons, the atoms, the solid stuff you are made of, can behave like waves. And this was not just one more curiosity to add to the pile. It cracked open the deepest puzzle of all, a puzzle that had been quietly threatening to bring down the whole of physics. The puzzle of why there is any solid world at all, why atoms hold together, why you exist. To feel the force of it, go back a few years to around the year 1911, when a physicist named Ernest Rutherford worked out the basic shape of the atom. He found that an atom is almost entirely empty space. Nearly all of its matter is gathered into a tiny, dense core at the center, the nucleus, carrying a positive electric charge, and around that core, somewhere out in the vast surrounding emptiness, are the electrons, carrying negative charge. It was natural to picture it like a tiny system of planets circling a small central star, the electrons swinging in their orbits around the nucleus. But that picture, by the rules of the old, trusted physics, was a catastrophe. Because an electron swinging in a circle is always changing its direction, and a charged thing that is constantly changing direction is, by the well-tested laws of the time, constantly bleeding away its energy as light. So the orbiting electron should be pouring out energy every instant, and as it lost that energy, it should spiral inward, faster and tighter, winding down like water circling a drain, until it crashed into the nucleus, and the atom simply ceased to exist. And when you did the arithmetic, the collapse was not slow. It would not take billions of years, or thousands, or even one. By the old physics, every atom in the universe should wind down and collapse in about 100 billionth of a single second. Sit with what that means. By the rules everyone trusted, the solid world should not last even an instant. Every atom should have collapsed almost the moment it formed. There should be no stable matter anywhere. No chemistry, no rock, no water, no stars, no planets, and no you lying here listening. The most basic fact about the world, that it is here at all, that it holds together, was something the finished, confident physics of the 19th century flatly could not allow. And yet here it all is. Atoms are stable. They last for billions of years. The first person to force a way through this was Niels Bohr, who in the year 1913 simply declared boldly and without any deeper justification a new rule. Electrons, he said, are not allowed to spiral. They can only occupy certain specific orbits, certain fixed rungs, like the rungs of a ladder. An electron can rest on a rung, and it can jump from one rung to another, giving off or taking in a precise packet of light when it does, exactly the kind of packet Planck and Einstein had found. But it cannot drift smoothly inward between the rungs, and there is a lowest rung of all, a floor, below which it cannot fall, and so it can never spiral into the nucleus. The atom holds. Bohr's rule worked. It even predicted exactly the particular colors of light that glowing hydrogen gives off. But like Planck's packets, it was a reluctant patch, a rule that worked for reasons no one could explain. Why should an electron be confined to certain rungs and forbidden the spaces between? It was de Broglie's wave of matter that finally answered. If the electron is also a wave, then only certain orbits can exist. The ones where the electron's wave fits a whole number of its ripples neatly around the loop and closes smoothly back onto itself. Just as a guitar string, held at both ends, can only sound certain clear notes. The ones whose waves fit the string. An electron can only settle into the orbits whose waves fit the loop. An orbit that did not fit would have the wave cross itself out of step and cancel itself into nothing, and so it simply cannot be. Bohr's mysterious rungs, it turned out, were nothing more than the orbits where the electron wave rings like a held note. The strange ladder was musical all along. Atoms are stable, and matter exists. And you are here, because the electron is a standing wave that can only ring at certain pitches, and at its lowest note it can ring forever without falling. So the solidity of everything around you, the chair, the floor, the warmth of your own body, does not rest on tiny solid pellets in orbit the way it might seem. It rests on standing waves, ringing in fixed notes, holding their shape. That is the only reason any of it lasts longer than 100 billionth of a second. The strangeness is not decoration on top of the solid world. It is the thing that makes the solid world possible at all. But all of this took years to fully understand, and it has raced us ahead of where our story stands. Let us come back to Einstein and let the irony settle in, because it is one of the quiet pleasures of this whole story. For this work, for the photoelectric effect, for the particle of light, Albert Einstein was awarded the Nobel Prize. Not for relativity, the thing he is most famous for this. The official recognition, when it came in the year 1921, named his discovery of the law of the photoelectric effect, the work that helped lay the foundation of quantum mechanics. Sit with that. The Nobel Prize that Einstein won, the highest honor in science, he won for helping to build the quantum theory. He was not a bystander to this revolution. He was one of its founders. He gave it one of its first and most important stones. Along with Planck, he is one of the people most responsible for the very existence of the idea we are following tonight. And he would spend the last 30 years of his life trying to prove that it could not be true. That is the heart of the matter. And it is worth being precise about, because it is easy to get wrong. Einstein did not turn against quantum mechanics because he failed to understand it. No one understood it better. He did not deny that its mathematics worked, that its predictions came true. He admitted all of that freely. What he could not accept, what he fought against until the day he died, was what the theory seemed to be saying about the deep nature of reality. Because as the theory grew, in the hands of the younger physicists who came after him, it began to insist on things that Einstein found intolerable, that the universe is, at its core, governed by chance, that nothing is fully real until it is measured, that God, as he would famously put it, plays dice. Einstein believed in a real world, a definite world, a world that is there, solid and decided whether or not anyone is looking at it. A world where, if things seem random, it is only because we do not yet know enough, and where a deeper layer of orderly clockwork is always waiting underneath to be found. The quantum theory he had helped to start was about to deny him all of that, and he never made his peace with it. But all of that lay in the future. In 1905, the revolution was barely beginning, and its strangest chapter had not yet been written. To reach it, we have to follow the trail from light into matter, and into a single experiment so simple that you could almost set it up on a kitchen table, and so deeply unsettling that physicists are still, a century later, arguing about what it means. It is, by a wide margin, the most important experiment in this entire story. It has been called the most beautiful experiment in all of physics, and it is where we are going next. So before we go on, let yourself sink a little deeper into the quiet. There is no hurry. The packets of light have been arriving faithfully for 100 years and more, and they will keep arriving long after tonight. Let the day you have had drift a little further behind you, and when you are ready, we will walk together toward two thin slits cut in a barrier, and the gentle, patient experiment that took the solid world apart. To understand the experiment we are about to walk into, you first need to understand what waves do when they meet. So let us begin somewhere calm and familiar, a still pond and a stone. Drop a single stone into still water, and you know exactly what happens. Rings spread out from the spot where it fell, circle after circle, traveling outward across the surface. That is a wave. Now drop 2 stones at once, a little apart, and watch what happens where their ripples meet. The 2 sets of rings spread into each other and overlap, and in the place where they overlap, something orderly and beautiful appears. In some spots, the crest of one wave lines up with the crest of the other, and they add together into a taller crest. In other spots, the crest of one lines up with the trough of the other, the high part meeting the low part, and they cancel each other out completely, leaving the water flat and still. You get a crisscrossing pattern across the surface, lines of strong rippling and lines of dead calm alternating. Physicists call this interference. It is the unmistakable signature of waves. When you see that pattern of alternating strong and cancelled bands, you know beyond doubt that waves are at work. Only waves do this. Particles, little solid pellets, cannot. Hold that picture. The alternating bands, the fingerprint of a wave. We are going to need it. Now to the experiment. It is, in its bones, very simple. So simple that a version of it was first performed more than 200 years ago by a man named Thomas Young around the year 1804, and it was Young's version that first convinced the world that light is a wave. Here is the setup. You take a barrier, a wall, and you cut 2 thin parallel slits in it, close together, 2 narrow vertical openings. On one side of the barrier, you put a source of light. On the other side, some distance back, you put a screen, a wall, where the light that comes through the slits can land and be seen. Light passes through the 2 slits, travels on, and strikes the screen. And the question is simply, what pattern does it make when it lands? If light were a stream of little particles, little pellets, the answer would be obvious. The pellets that happen to be heading toward one slit go through it and make a bright stripe on the screen behind that slit. The pellets heading toward the other slit make a second bright stripe behind that one. 2 slits, 2 stripes. Simple. But that is not what you see. What you see on the screen is not 2 stripes. It is the pattern of the pond. Many bands. Bright, dark, bright, dark, bright, dark, alternating across the screen, fading out at the edges. The light coming through the 2 slits is interfering with itself, exactly like the 2 sets of ripples on the pond. Where the waves from the 2 slits arrive in step, they add together and you get a bright band. Where they arrive out of step, they cancel and you get darkness. This is the experiment that proved 2 centuries ago that light is a wave. The bands are the wave's fingerprint, and there they are, plain on the screen. So far, so settled. This is 19th century physics, comfortable and clear. But now we bring in everything we learned tonight from Einstein, and the floor begins to tilt. Because we now know that light is also made of particles, of photons, of those indivisible packets. So let us turn the light source down. Let us turn it down further and further, until it is so faint, so dim, that it is sending out the photons one at a time. A single packet of light leaves the source, crosses to the barrier, and then, whatever it does there, travels on and strikes the screen and makes a single tiny dot where it lands. Then, a moment later, the next single photon. And the next, one lonely particle of light at a time, each one making its own single dot on the screen, like a single drop of rain landing on dry pavement. Now, with the light this faint, each photon is alone. There is only one photon crossing the apparatus at any moment. There are no other photons for it to interfere with, no second set of ripples to meet. It is a single particle, traveling by itself, landing as a single dot. So surely now, with the photons arriving one at a time as lonely individual particles, the wave pattern must disappear. Surely now, we will just see them pile up into two simple stripes. One behind each slit, the way particles should. So we run the experiment. We send the photons through, one at a time, and we let the dots accumulate on the screen, slowly, over hours. At first it looks random. A dot here, a dot there, scattered, no pattern. But as the dots build up, as thousands and then millions of single lonely photons each make their single mark, a shape begins to emerge from the scatter. And the shape that emerges, dot by patient dot, is the bands, the interference pattern, the fingerprint of the wave. Bright, dark, built up out of millions of individual particles that each arrived alone. Stop and feel how impossible this is. Each photon went through the barrier by itself, with no other photon anywhere near it. Each one landed as a single particle, a single dot. And yet the pattern they built up together, over time, is the pattern of waves interfering, of something passing through both slits at once and overlapping with itself. But each photon is a single, indivisible packet. It cannot split in half. So how can a single photon, going through the barrier alone, produce a pattern that requires something to pass through both slits at the same time and interfere with itself? There is only one answer the mathematics will allow, and it is the answer that ends the solid, sensible world. Each single photon goes through both slits at once, not half through one and half through the other. The whole of it, somehow, takes both paths at the same time, travels through as a spread-out wave of possibility that passes through both openings, overlaps with itself on the far side, and only then, at the screen, gathers itself back into a single dot in a single place. Each lonely photon interferes with itself, because on its way across, it was not in one place at all. It was a wave of where it might be, exploring every path at once. This is not a trick of having many particles. We proved that by sending them one at a time. This is not poor equipment or a flaw in the experiment. This experiment has been done and redone and refined for a century with light, and then, astonishingly, with electrons, with whole atoms, even with large molecules made of hundreds of atoms. Matter itself, the solid stuff de Broglie wondered about, does exactly the same thing. Send electrons through two slits one at a time, and they too build up the bands. Each electron, it seems, passes through both slits at once and interferes with itself. The thing you are made of does this. And now comes the part that turns a beautiful mystery into something genuinely unsettling. The part that troubled Einstein to his bones. We naturally want to ask, well, which slit did it really go through? It must have really gone through one of them. So let us just look. Let us be clever. Let us place a tiny detector at the slits, a little instrument that can sense each photon as it passes and tell us, for each one, which slit it actually went through. We are not going to block anything. We are just going to watch. We are going to catch the universe in the act and settle this once and for all, which slit. So we set up our detector and we watch the slits and we run the experiment again. And the moment we do, the moment we successfully detect which slit each photon goes through, the interference pattern vanishes. It simply disappears. The bands are gone. Instead, On the screen, we now get exactly what we expected for particles in the first place. Two simple stripes, one behind each slit. The instant we find out which path each photon takes, each photon stops going through both slits and goes through only one, like an ordinary particle, and the wave pattern dies. And if we switch the detector off again, if we stop looking, stop asking which slit, the bands come right back. Look, and you get particles, two stripes. Do not look, and you get waves, many bands. The pattern on the screen depends on whether or not you tried to find out which way the photon went. Read that again, slowly, in the quiet, because it is one of the strangest facts human beings have ever confirmed about the world. Whether the photon behaves like a wave that goes through both slits, or like a particle that goes through one, depends on whether you are watching. The act of finding out which path it took changes what it does. The universe behaves one way when it is observed, and another way when it is not. And one thing must be made clear here, because it is the single most misunderstood point in this whole subject. This has nothing to do with a conscious mind looking on. The detector does not need a person watching it. A camera left recording in an empty room collapses the pattern just the same. It is the physical act of measurement itself, the which path information being drawn out into the world by the instrument, that changes things, not anyone's awareness of it. This is the heart of the mystery. This is the thing that no one in 100 years has fully explained away. It is called, in the language of the theory, the measurement problem, and we will return to it more than once tonight. When the photon is not being watched, the theory does not describe it as being in one place or the other. It describes it as a wave of possibilities, a spread-out smear of every place it could be and every path it could take all at once. The theory has a name for this strange, smeared-out state of many possibilities held together at the same time. It is called superposition. The photon, unobserved, is in a superposition of going through the left slit and going through the right slit, both at once, and that is why it can interfere with itself. But the moment you measure it, the moment you look and find out where it actually is, all of those possibilities collapse instantly into a single, definite outcome. One slit, one place, one dot. The wave of maybes becomes a single, solid fact, but only at the instant of looking. Before that, the theory insists there was no single fact of the matter. There was no answer to the question which slit, because the photon had not gone through one slit. It had gone through both, as a wave, until you forced it to choose by looking. Now you can perhaps begin to feel what so disturbed Einstein, and what disturbs careful people still. We are used to thinking that things are how they are whether or not anyone is watching. The moon is in the sky whether or not you look at it. The cup is on the table whether or not you are in the room. The world is solid and definite, and there and you're looking at it merely informs you of a fact that was already true. That is the most basic intuition we have about reality. It is so deep we barely notice we hold it. And the double-slit experiment seems to say that this intuition is wrong. That at the smallest scales, things are not definite until they are observed. That a particle does not have a single position until you measure its position. That reality, underneath, is not a collection of solid facts, but a shifting cloud of possibilities that only settles into one definite outcome at the moment of measurement and dissolves back into a cloud of maybes the instant you look away. Einstein hated this. He could not bring himself to believe it. There must, he felt, be something more underneath. The photon must really go through one slit or the other. There must be some hidden detail, some piece of information the theory was missing. that decides the matter in advance so that the world stays solid and real and decided whether or not anyone is watching. The randomness, the dependence on observation, all of it must be a sign that quantum mechanics, for all its success, was an incomplete theory. A true and deeper theory, he believed, would restore the solid world, would put the moon back in the sky when no one is looking. He spent decades searching for that deeper theory. And tonight, later, we will find out how that search ended in an experiment he did not live to see. For now, it is enough to sit with the two slits and the screen and the bands that come and go depending on whether you watch. It is enough to know that this experiment is real, that it has been done thousands of times, that the device you are using to hear these words could not function if this strange behavior of matter were not true. The grainy, watchful, possibility-laden world of the quantum is not a story. It is the flaw beneath everything. So let the day go a little further. Let the solid world loosen its grip just slightly. The cup is still on the table. The moon is still in the sky. At your scale, the scale of cups and moons and warm beds, the strangeness averages out, and the world stays reassuringly firm beneath you, which is why you have never once noticed any of this in your ordinary life. The weirdness lives down below, in the small places, holding everything up. You may rest your whole weight on it, exactly as you always have. And as you settle, we will go down one level further and meet the man who wrote the equation that describes this wave of possibility and the most famous imaginary cat in the history of the world. By the middle of the 1920s, the strange ideas we have been gathering, Planck's packets, Einstein's particles of light, de Broglie's waves of matter, the spread-out cloud of possibility behind the double slit, all of it was swirling together, unfinished, in the minds of a small group of mostly young physicists across Europe. It needed to be turned into a real theory, a proper machinery, with equations that could make predictions. And in an astonishing burst of work, over just 2 or 3 years, that is exactly what happened. Two men, in particular, each found a way to write the new physics down. And though they came at it from completely different directions, their two versions turned out to be underneath the very same theory. The first was a young German named Werner Heisenberg, who in the year 1925, while recovering from hay fever on a barren island in the North Sea, found a strange new mathematics for the quantum world. And out of his way of looking at things came a result so important and so unsettling that it has become one of the few pieces of this whole subject that almost everyone has heard of. It is called the uncertainty principle. Here is what it says. There are certain pairs of things about a particle that you cannot both know perfectly at the same time. The most famous pair is position and motion, where a particle is and where it is going. And the uncertainty principle says that the more precisely you pin down one of these, the more hopelessly blurred the other must become. If you know exactly where a particle is, then its motion, its speed and direction becomes completely undefined, wild, unknowable. If you know exactly how a particle is moving, then its position smears out across all of space, and you cannot say where it is at all. You can trade a little knowledge of one for a little knowledge of the other, but you can never have both in full. There is a hard limit woven into the fabric of things on how much can be known about a particle at once. Now, it is tempting to hear this and think it is simply a problem of clumsy instruments, as though the particle really does have a definite position and a definite motion both at once, and we are just too ham-fisted to measure them without disturbing things. That is the natural assumption, and it is what many people quietly believe the uncertainty principle means. But it is not what it means, And the difference is everything. The uncertainty principle is not a statement about the limits of our measuring tools. It is a statement about the way the world actually is. The particle does not have a definite position and a definite motion at the same time. Not hidden from us, not merely unmeasured. It does not have them. A particle with a perfectly definite position simply does not possess a definite motion, in the same way that a circle does not possess corners. It is not that the corners are there, but hard to find. There are no corners. The sharpness we are used to, the idea that everything has all of its properties pinned down to exact values at every moment, turns out to be something the universe does not honor at the smallest scales. Down there, things are inherently fuzzy, not fuzzy to us, fuzzy in themselves. This is, once again, the kind of statement that Einstein could not abide and that troubles thoughtful people still. But the experiments are merciless on this point. The fuzziness is real, and it is not in our instruments. It is in the world. The second man was an Austrian named Erwin Schrodinger, and in the year 1926, working from de Broglie's idea that matter is somehow wave-like, he wrote down an equation. It is the central equation of all of quantum mechanics, as important to this subject as Newton's laws were to the old physics, and physicists use it every single day. You do not need its symbols tonight. You only need to know what it does. Schrodinger's equation describes that wave of possibility we met at the double slit. Physicists call this wave the wave function. It is the mathematical object that holds, all at once, every possibility for a particle, every place it might be found, every outcome a measurement might give, each with its own likelihood. And Schrodinger's equation tells you, with perfect precision, how that wave of possibility flows and changes and evolves through time. Given the wave function now, the equation tells you exactly what the wave function will be later. It is, in that sense, as clean and as predictable and as deterministic as anything in old-fashioned physics. The wave of maybes rolls forward through time in a completely lawful way. And here is the deep strangeness, the crack that runs through the very center of the theory and has never been sealed. The equation describes the smooth, lawful, predictable flow of a wave of many possibilities, all coexisting. But whenever we actually measure something, whenever we look, we never find many possibilities. We find one, a single, definite outcome, one position, one dot on the screen, one reading on the dial. The wave of maybes, which the equation so beautifully describes rolling along somehow at the instant of measurement, collapses down to a single one of its possibilities, and all the others simply vanish. The equation does not describe this collapse. The smooth, lawful evolution and the sudden collapse at the moment of measurement are two completely different kinds of behavior, and the theory has only ever explained the first one. The second, the collapse. The moment when the cloud of maybes becomes a single fact we put in by hand, because that is what we observe. But we cannot say what it is, or why it happens, or what counts as a measurement, or where exactly the line falls between the quantum world of coexisting possibilities and the ordinary world of single definite facts. This is the measurement problem again, now seen from the inside of the equation itself. It was this very problem, this absurd-seeming business of coexisting possibilities collapsing when observed, that drove Erwin Schrödinger himself to dream up the single most famous image in all of quantum physics. And here is the thing that almost everyone gets backward, so let us be careful and get it right. Schrödinger did not invent his famous cat to celebrate how wonderful and strange quantum mechanics is. He invented it to mock the theory, to show how ridiculous it became when you followed it honestly. The cat was a weapon. aimed at the heart of the new physics, and he sharpened it in letters with his friend, who happened to be Albert Einstein, the two of them encouraging each other in their shared discomfort with what the younger physicists were claiming. Here is the thought experiment, as Schrodinger laid it out in the year 1935. Imagine a cat sealed inside a steel box where you cannot see it. Inside the box with the cat, you place a single atom of a radioactive material, the kind that might or might not decay and give off a particle in the next hour. Whether it decays is a purely quantum event. It is governed by exactly the wave of possibility we have been describing. Over an hour there is, say, an even chance that the atom decays and an even chance that it does not. Now you rig up a cruel little machine. If the atom decays, a detector notices the particle and triggers a hammer, which breaks a flask of poison which kills the cat. If the atom does not decay, nothing happens, and the cat lives. So the cat's fate is tied directly to the quantum coin flip of the single atom. Atom decays, cat dies. Atom holds, cat lives. And here is Schrodinger's barb. According to the theory, taken honestly, before you open the box and look, the atom is not in one state or the other. It is in a superposition, that smeared together state of both possibilities at once. It is both decayed and not decayed, both at the same time, just like the photon going through both slits, but the atom's fate is wired to the cat's. So, if the atom is in a superposition of decayed and not decayed, then the cat, following the same logic, must be in a superposition too, a superposition of dead and alive, not dead and not alive, and not simply one of the two unknown to us. Both at once, a cat that is genuinely, simultaneously dead and alive, smeared across both possibilities, until the moment someone opens the box and looks, at which instant the wave of maybes collapses and the cat becomes, suddenly, definitely one or the other. Schrodinger's point was, this is plainly absurd. A cat is a large, ordinary, everyday thing. The idea of a cat that is both alive and dead at the same time is nonsense. We never see such things. And so, he was arguing, there must be something wrong, or at least something badly incomplete, about a theory that, followed to its logical end, produces dead and alive cats. He was on Einstein's side. He was using the cat to say, look how ridiculous your theory becomes when you take it seriously. But here is the twist of history, and it is a strange one. The cat did not destroy the theory survived. The cat, instead, became the single most beloved illustration of quantum weirdness ever devised, repeated endlessly, usually by people who have no idea it was meant as a criticism. And worse, for those who wanted the strangeness to go away, the basic phenomenon at its core turned out to be real. We cannot, in practice, put a whole cat into a superposition because large, warm objects interact with their surroundings far too quickly and constantly for the delicate state to survive, a process we now understand reasonably well. The cat is protected from its own weirdness by its size and its constant contact with the world. But for small, isolated things, atoms, particles, and now, in careful modern laboratories, for apparatus of atoms, the superposition is absolutely real. We can place a particle in a superposition of two states and keep it there, and do experiments that prove it really was in both at once. The dead and alive logic that Schrodinger thought was a reduction to absurdity is, at the small scale, simply how things are. He built the cat to break the theory. The theory ate the cat and asked for more. So the question Schrodinger raised so sharply still hangs in the air, unanswered. Where exactly is the line? At the scale of single atoms, superposition is real and constant. At the scale of cats, the world is solid and definite and singular, and a cat is only ever simply alive or simply dead. Somewhere between the atom and the cat, the strangeness fades out and the ordinary world takes over. But the theory does not tell us where that line is, or why it is there at all, or what truly happens at the moment a smear of possibilities becomes a single fact. We have learned a great deal about how the fading happens, about why big things lose their quantum strangeness so fast. But the deepest version of the question, the one about that final collapse into a single definite outcome, remains exactly as open as it was when Schrodinger sealed his imaginary cat in its box, almost a century ago. This was where things stood as the 1930s arrived, a theory of impossible success and impossible strangeness. A wave of possibilities, evolving in perfect lawful order and then collapsing, no one could say how, into single facts whenever the world was observed. A universe that seemed to deal in chance at its very foundations. And two of the greatest minds alive, Einstein and Schrodinger, standing against it, certain in their bones that it could not be the final word, that the solid old world must be hiding somewhere underneath. Einstein was about to make his most serious attempt to prove it. He was going to design, with two younger colleagues, a single sharp argument meant to show, once and for all, that quantum mechanics was incomplete, that there had to be a deeper, saner reality underneath. It was the best objection anyone had ever raised against the theory. It was so good that it took the world nearly 30 years to figure out how to answer it. And when the answer finally came, long after Einstein was gone, it did not go the way he was sure it would. That argument, and that long-delayed answer, is the turning point of our whole story. But it can wait until you have rested a while in the strangeness we have already gathered. The fuzzy particle, with no sharp position and motion at once, the wave of maybes rolling lawfully along, the cat in the box, neither one thing nor the other. Let these sit with you softly, asking nothing. There is no box you need to open tonight. There is no measurement you need to make. You can let every possibility stay open, uncollapsed, and simply drift, while we gather ourselves to follow Einstein into his last great argument with the universe. For most of the late 1920s, the argument over quantum mechanics had a kind of home, and two great champions. The home was a series of grand scientific gatherings in Brussels, and the two champions were Albert Einstein, defending the old solid world, and a Danish physicist named Niels Bohr, defending the strange new one. Bohr was, in many ways, the spiritual leader of the younger generation, the ones who had built the new theory and were prepared to accept its strangeness as simply the truth about nature. He had developed a whole way of thinking about the quantum world, a philosophy of it that came to be called the Copenhagen interpretation after the city where he worked. We will look at what it actually claims a little later tonight. For now, it is enough to know that Bohr was prepared to give up the solid, definite, observer-independent world, to say that yes, properties are not fixed until measured, and yes, the universe deals in genuine chance, and no, there is no deeper clockwork hiding underneath. That is just how reality is, Bohr said, and our discomfort with it is our problem, not nature's. Einstein could not accept this, and he attacked it with everything he had. At these gatherings, over breakfast, he would arrive with a new thought experiment, a clever, imaginary device designed to beat the uncertainty principle, to show that you could, in fact, pin down both of a particle's fuzzy properties at once, and so prove the theory wrong. And each time, Bohr would go away and think and by dinner he would return, having found the flaw, having shown that Einstein's clever device would not work after all, that the uncertainty held. Day after day, Einstein would attack, and Bohr would defend, and the theory survived. It is one of the great intellectual duels in the history of science. Two brilliant and deeply opposed minds circling the strangest idea anyone had ever had. It was somewhere in this long argument that Einstein gave the objection its most famous form. He simply could not believe that the universe, at its root, was a matter of chance. That when an atom decays, or a photon strikes a screen, there is no hidden reason, no underlying cause, that the outcome is simply, fundamentally random, decided by nothing. In a letter to a friend and fellow physicist, Max Born, Einstein put it in words that have echoed ever since. He wrote that the theory said a great deal, but did not really bring us any closer to the secret of the old one, and then he added the line, "Everyone remembers." He was convinced, he said, that God does not play dice. Bohr is said to have replied, with some exasperation, that Einstein should stop telling God what to do. The line may be polished by retelling, but the disagreement behind it was real and total. Einstein wanted a universe of hidden reasons. Bohr offered a universe of irreducible chance. And for years there seemed no way to decide between them by any experiment. It looked like a question of philosophy, of taste, of what kind of universe each man was willing to live in. Untestable. A matter for argument over dinner, forever. And then, in the year 1935, Einstein and two younger colleagues, Boris Podolsky and Nathan Rosen, published a short paper that changed the character of the whole debate. It is one of the most important papers in the history of physics, and it is known forever after by the initials of its three authors, the EPR paper: Einstein, Podolsky, Rosen. The title was a question. Can the quantum mechanical description of physical reality be considered complete? And their answer was a careful, devastating no. To make their case, they reached for the strangest feature of the whole theory. A feature so strange that Einstein clearly believed no reasonable person could accept it, and that it therefore proved the theory must be incomplete. We now call this feature entanglement. And it is, even today, the single deepest and most baffling thing in all of quantum physics. So let us build it slowly. The theory allows you to take two particles and prepare them together in a single shared quantum state so that their properties become linked, tied together, entangled. Once two particles are entangled in this way, you can no longer describe them separately, as two independent things, each with its own properties. The theory describes them as one combined system, a single wave of possibility covering both of them at once, with their fates braided together. Here is what that braiding means in practice. Suppose you prepare two such particles so that a certain property of theirs must always come out opposite. If one is measured to be up, the other must be down. If one is down, the other must be up. They are perfectly anti-matched. But, and this is the crucial part, before measurement, neither particle has a definite value of this property at all. Each one, on its own, is in a superposition, a smear of both up and down at once, exactly like the photon at the slits. Neither is anything definite yet. There is only the strict rule binding them, that whatever they turn out to be, they will turn out opposite. Now, you take these two entangled particles and you separate them. You send one to the far side of the room, or the far side of the country, or, in principle, the far side of the galaxy. They can be any distance apart at all. The braid between them, the theory says, does not weaken with distance. It does not stretch or fade. It simply holds. And now you measure one of them. the one in front of you. You look, and the smear of possibility collapses, and your particle becomes, say, definitely up. Random, 50-50, no way to predict it in advance. It comes out up, fine. But the instant it does, with total certainty, that the other particle, the distant one, light years away perhaps, is now definitely down. It must be. The rule demands it. And here is the knife edge that Einstein pressed on. According to the theory, that distant particle was not down before you measured yours. It was an undecided smear of both, just like yours, until the very instant of your measurement. And then, the moment you collapsed your particle to up, the distant one collapsed to down instantly. Across any distance, with nothing traveling between them. Your act of looking, here, seemed to reach out across the whole gulf of space and settle the state of a particle arbitrarily far away, in no time at all. This was, to Einstein, simply unbelievable. He had a name for it, a dismissive, almost mocking name. He called it spooky action at a distance because it looked like magic. It looked like one particle instantly affecting another, across any distance, faster than light, faster than anything, with no mechanism, no signal, no connection. And Einstein had spent his life establishing that nothing, no influence, no information, can travel faster than light. The idea that measuring one particle could instantly reach across the galaxy and decide the state of another offended the deepest principle of his own great work. So Einstein, Podolsky, and Rosen offered what they considered the only sane conclusion. The spooky action, they argued, is not real. It is an illusion, and the way to dissolve the illusion is obvious. The two particles must have simply had their definite values all along. From the moment they were separated, this one was already up, and that one was already down. Secretly, all the way through. They carried their answers with them, like a pair of gloves separated into two boxes and shipped to opposite ends of the earth. Open one box, find the left glove, and you instantly know the far box holds the right glove. But nothing magical happened when you looked. The gloves were always left and right. You merely uncovered a fact that was already settled. No spooky action, no faster-than-light anything, just hidden information, decided in advance. But here is the thing. Quantum mechanics flatly denies that the particles had definite values all along. It insists they were a genuine, undecided smear until measured. So, Einstein argued, if the particles really did carry hidden, predetermined values, and if quantum mechanics says they did not, then quantum mechanics is leaving something out. It is an incomplete description of reality. There are real things going on, the hidden, predetermined values, that the theory does not include. Therefore, a deeper, more complete theory must exist underneath it, one that does include those hidden values and restores a sane, local, solid world where nothing has to reach across the galaxy in an instant. This deeper theory, this missing layer, came to be called a hidden variable theory. The hidden variables were the secret, predetermined answers the particles were supposedly carrying all along. It was a beautiful argument. It was sharp and clear, and it seemed almost airtight. It put Einstein's objection on the firmest possible ground. Either you accept ridiculous, spooky action at a distance, or you accept that the particles had hidden, predetermined values and that quantum mechanics is incomplete. And since spooky action was, to Einstein, obviously absurd, the conclusion was forced. The theory was incomplete. There was a deeper, saner reality underneath. The solid world was saved. Bohr responded, defending the theory, insisting that the EPR argument smuggled in assumptions about reality that the quantum world simply does not obey. But his response was murky, difficult, and unsatisfying to many. For a long time, it seemed as though Einstein had landed a genuine blow and that the matter could not really be settled because the whole disagreement still seemed untestable. Both pictures, the spooky action picture and the hidden variable picture, predicted exactly the same results for any experiment anyone could think of. They agreed on every observable outcome. They differed only in the story they told underneath. And if two pictures predict the same results for every possible experiment, then no experiment can tell them apart. It looked once again, like philosophy, a matter of taste, untestable, perhaps forever. Einstein died in the year 1955, holding to his conviction. He died believing that quantum mechanics, the theory he had helped to found, was a true but incomplete description of the world, that the spooky action was an illusion, that a deeper layer of hidden variables was waiting to be found, and that when it was found, the solid, local, definite world of his deepest intuition would be restored and God would be shown, after all, not to play dice. He went to his grave certain of it, and certain that the question could probably never be decided by experiment at all. He was wrong about that last part. The question could be decided by experiment. Einstein simply did not live to see how. 9 years after his death, a quiet physicist from Northern Ireland, working almost as a hobby on the side, would find the thing everyone had missed. He would find a way to tell the two pictures apart. A real, concrete, physical experiment whose result would come out one way if Einstein was right and the particles carried hidden predetermined values, and a different way if quantum mechanics was right and the spooky action was real. After 30 years of looking like a matter of pure philosophy, the deepest question about the nature of reality was about to become a thing you could test on a laboratory bench. His name was John Stuart Bell, and what he found and what the experiments revealed when they were finally able to perform his test is the heart of everything we have been walking toward tonight. So gather yourself gently in the dark. Rest a moment longer in the open question, the way Einstein never could. And when you are ready, we will go and find out which man was right about the universe. The man who broke the deadlock did not do it for a living. John Stuart Bell spent his days working on the design of particle accelerators. The deep questions of quantum mechanics was something he thought about on the side, in his own time, almost privately, because they nagged at him. He took Einstein's worry seriously. He found the spooky action genuinely troubling, and he suspected, like Einstein, that there might be a sane, hidden variable world underneath. He set out to study exactly what such a world would have to look like. And in the year 1964, while thinking this through, Bell discovered something that everyone, including Einstein, had missed. Something that had been hiding in the problem for 30 years. He found that the two pictures, Einstein's hidden variable world and the strange quantum world, do not, after all, predict exactly the same thing for every possible experiment. There is a particular kind of measurement, a clever one, where they disagree, where they give different numbers. And so the question of which one is true is not philosophy at all. It is a thing you can measure. This is Bell's theorem, and it is one of the most profound results in the history of science. So let us go gently and get the shape of it. The trick is not to measure the entangled particles in just one fixed way. The trick is to measure them at a variety of different angles, different settings, and to do it many, many times over thousands and thousands of entangled pairs, and then to look not at any single result, but at the statistics, at how often the two distant results match, and how that matching changes as you vary the angles. Now here is the heart of what Bell proved. Suppose Einstein is right. Suppose every particle carries hidden, predetermined answers set in advance, locally, before it ever leaves home, with no spooky action of any kind. Bell showed that in any world like that, any world of local predetermined values, the statistics of those matchings are bound by a strict limit. There is a certain amount of agreement between the distant measurements that such a world simply cannot exceed. No matter how the hidden values are arranged, no matter how cleverly nature sets them in advance, the correlations can only be so strong and no stronger. This ceiling is called a Bell inequality. It is a hard limit, a wall that any local hidden variable world, any world of the kind Einstein wanted, must obey. And then Bell calculated what quantum mechanics predicts for the very same measurements. And quantum mechanics, with its entanglement, its spooky braiding, its smear of shared possibility, predicts correlations that go beyond that limit. Stronger agreement than any local predetermined world could ever produce. Quantum mechanics breaks through Bell's wall. The two pictures give different numbers, and the difference is measurable. So now, there was a real, concrete test, with a clear verdict on either side. Take many entangled pairs, measure them at varied angles, far apart, count up the correlations. If the result stays under Bell's limit, then Einstein could be right. The particles could be carrying local hidden answers. The solid world survives. But if the result breaks through Bell's limit, then no local hidden variable world is possible. The particles cannot have carried predetermined local answers. The spooky action, or something at least as strange, is simply real, woven into the world, and there is no sane local clockwork hiding underneath after all. After 30 years of looking like a matter of taste, the deepest question about the nature of reality had become an experiment. All someone had to do was perform it. It was not easy. You need to make pairs of entangled particles reliably, usually particles of light, send them far apart, measure them at rapidly chosen angles, and do it cleanly enough, and often enough, that the statistics are beyond doubt. It took technology that barely existed. The first real attempts came in the early 1970s, when an American physicist named John Clauser, working with a colleague, built an apparatus to test Bell's idea for the first time and found the first signs that Bell's wall was indeed being broken, that quantum mechanics was winning. But the early experiments had gaps, loopholes, ways that a determined believer in hidden variables could still, just barely, wriggle out. The decisive step came at the start of the 1980s, in France, in the work of a physicist named Alain Aspect. Aspect designed a version of the experiment far more careful than anything before. His most important refinement was this: a skeptic could always worry that somehow the two distant measuring devices, or the particles, were secretly in contact, quietly coordinating their answers through some ordinary signal passing between them, which would let a clever local hidden variable scheme fake the quantum result. So Aspect arranged to change the angle of each measurement at the very last instant, while the particles were already in flight, too late for any signal traveling at the speed of light to pass between the two sides in time to coordinate. He slammed that door. He made it so the two measurements could not be in cahoots without sending something faster than light, which Einstein himself had forbidden. And the result, when it came, in the year 1982, was clear and clean and final. Bell's wall was broken. The correlations soared past the limit that any local predetermined world could ever reach, and landed exactly where quantum mechanics said they would. The experiment came down decisively on the side of the strange new world and against Einstein's hope. Let us say plainly what this means, because it is the destination of our whole night, and it deserves to be stated without hedging, and then stated again with care. Without hedging, Einstein was wrong. The thing he was sure of, the thing he carried to his grave, the belief that the particles must have had their definite answers all along, set locally in advance, with no spooky action. The belief is not merely unproven, it is ruled out. The universe has been asked the question directly, though, in the most careful way we know how to ask it, and the universe has answered that no local hidden, the particles do not carry sane, predetermined, local answers. The spooky action, the instantaneous braiding across distance, or something every bit as strange is genuinely real. Einstein's deepest intuition about the nature of reality, the solid local world humming along whether or not anyone looks, was tested by experiment, and it failed. Now with care, because the precise shape of his wrongness matters, and on a story like this one, precision is the whole point. 3 things are worth holding clearly. The first, what was ruled out is specifically a local world of hidden variables. The word local is doing enormous work. It means, roughly, that nothing influences anything else faster than light, that each particle minds its own business, carrying its own properties, untouched by distant events. That is the world the experiments destroyed. There do still exist versions of quantum theory that restore definite predetermined values to the particles, but they buy that solidity at a terrible price. They have to allow exactly the instantaneous, faster-than-light connectedness that Einstein found intolerable. So you may keep a definite world, or you may keep a local world where nothing reaches across space in an instant. The experiments say you cannot keep both, and the local world was the one Einstein truly could not bear to lose. The second, this strange connectedness, real as it is, cannot be used to send a message. This is subtle and important, and it is where many breathless accounts go wrong. When you measure your entangled particle and it collapses the distant one, you cannot use that to transmit any information faster than light. The reason is that your own result is purely random, 50-50, out of your control. You cannot choose what you get, so you cannot send a signal in it. The distant partner sees only their own random-looking string of results, with no message in it, until the two of you later compare notes through an ordinary channel no faster than light and discover the eerie matching after the fact. So the spooky correlations are real, but they are non-signaling. They do not let us send anything faster than light. Relativity, Einstein's own great theory, survives intact, even here. The universe is stranger than he wanted, but it has not contradicted itself. And the third, Einstein's greatness is not diminished by being wrong here. It is almost the opposite. His objection was so deep, so precisely aimed, that it forced the question into a form that could finally be tested. The EPR paper, written to expose a weakness in the theory, instead handed physics the tool that would prove the theory right. Bell built his theorem directly on Einstein's argument. Without Einstein's beautiful wrong intuition, we might never have learned how to ask the question at all. He pointed at the strangest thing in the theory and said, "This cannot be real." And in pointing at it so clearly, he showed everyone where to look. The entanglement he raised up as the theory's fatal flaw turned out to be its deepest truth and is now the foundation of an entire new technology. The verdict has only grown stronger with time. Aspects experiments had their own small remaining loopholes, and over the following decades physicists closed them one by one until, in recent years, Experiments were performed that sealed every gap at once, leaving no escape whatsoever for a local, hidden variable world. The answer never changed. Every time, the quantum prediction wins. Every time, Bell's wall is broken. The result is now one of the most thoroughly confirmed facts in all of physics. And in the year 2022, the highest honor in science formally recognized this whole long arc. The Nobel Prize in Physics was awarded to 3 people: John Clauser, Elaine Aspect, and a third pioneer of these ideas named Anton Zeilinger, for their experiments with entangled particles, for establishing that Bell's inequality is truly violated, and for founding the new science of quantum information that has grown up around it. The prize was, in a real sense, the establishment of physics formally writing down the verdict. Oh, no. The strange world is the real one. The spooky action is real. Einstein, on the deepest question of his later life, was wrong. And we now know it as surely as we know almost anything. There is something quietly moving in the timing of all this, and it is worth resting on as this part of the night comes to a close. Einstein died in the year 1955. Bell found his theorem in 1964, 9 years too late for Einstein to have seen it. The decisive experiments came in the early 1980s, almost 30 years after Einstein's death. And the Nobel Prize came in 2022, 67 years after he was gone. The man whose objection made the whole thing possible never got to learn the answer. He spent the last decades of his life patiently certain that a saner world lay underneath, and he died still searching for it. And the search was, in the end, his one great and beautiful mistake. One wonders sometimes what he would have said if someone could have shown him the result. Whether he would have been disappointed, or, being the kind of mind he was, quietly delighted that the universe turned out to be even stranger than the strangest thing he had been arguing against. We cannot know, but we can sit with the fact itself, softly in the dark. 2 particles parted and sent to opposite ends of the world, somehow still answering as one, no signal between them. No hidden script. Just a connection that the universe permits and our minds were never built to picture, proven real by the most careful experiments we know how to do. It is true. It is simply, strangely true. And you do not have to understand it to rest beneath it. You only have to let it be what it is, the way the universe has all along. So let the argument settle now. Einstein and Bohr are both long gone, and the question they fought over has its answer. And the answer is gentler than it sounds, because it changes nothing about the warm and solid feel of the world you are lying in. The strangeness lives far below, holding everything up, asking nothing of you tonight. In a little while, we will come back up from these depths into the ordinary daylight world, and I will show you all the quiet places this impossible theory is already living, unseen, inside the most familiar objects of your life. But first, simply breathe and let the great old argument grow quiet and rest. We have spent the night out at the strange edges of this theory, among smeared-out particles and dead and alive cats and connections that cross the world in an instant. It would be easy to come away thinking quantum mechanics is a thing for laboratories and thought experiments, far from ordinary life. But that is exactly backward. This strange, unfinished, deeply puzzling theory is, by a wide margin, the most practically useful idea human beings have ever had. It is not out at the edges of your life. It is underneath the whole of it. So let us come up, slowly, from the deep water, and walk through the ordinary rooms of an ordinary day and notice where the quantum is hiding. It is hiding nearly everywhere. Start with the most obvious thing. The device you are using to hear these words. Whatever it is, a phone, a tablet, a computer, a speaker, somewhere inside it is a small, flat chip. And on that chip are carved billions of tiny switches called transistors. The transistor is the single most manufactured object in the history of our species. There are more transistors in the world than there are grains of sand on all the beaches of the earth, by a wide margin. And they are all doing the same simple job, switching on and off billions of times a second to do the counting that runs every digital thing you own. And the transistor works entirely because of quantum mechanics. It is built from materials called semiconductors, usually silicon, and the whole reason a semiconductor can be coaxed to switch between carrying current and blocking it, which is the one trick at the bottom of all computing, comes from the quantum behavior of electrons inside the material. The way electrons are allowed to occupy only certain energy levels, the way they fill those levels, the way a small voltage can open or close a path for them, all of it is governed by the rules we have been exploring tonight. No quantum mechanics, no transistor. No transistor, no computers, no phones, no internet, no digital world at all. The entire information age, the defining feature of the era you live in, is built on top of this theory that no one fully understands. Every message you have ever sent passed through billions of tiny quantum switches to reach its destination. Now look at light. Think of the thin red beam of a checkout scanner, or the laser in a disc player, or, far more importantly, the pulses of laser light that race through the glass fibers beneath the oceans, carrying nearly all of the world's communication. A laser is a quantum device through and through. Its name is even an abbreviation describing the quantum process that powers it, the way atoms can be made to release their stored energy as light, all in step, all the same color, all marching together in a single coherent beam. And here is a lovely thread back to where we began the night. The core idea that makes a laser possible, the way an atom can be triggered to release a particle of light, was first worked out in theory by Albert Einstein back in the year 1917. The same man again. He laid the groundwork for the laser decades before anyone built one. The light carrying this very recording across the world, if it traveled by fiber, was very likely riding on a quantum process Einstein himself first described. The same family of physics gives you the gentle glow of the screen in front of you if it uses the little lights called LEDs, which turn electricity directly into light through a purely quantum dance of electrons releasing energy. Those same small lights now fill your home, in bulbs that sip a tiny fraction of the power the old ones drank. And they do it by exploiting the quantum rules of how electrons shed energy as light. Every modern bulb of that kind is a small quantum machine glowing quietly on your ceiling. Go to a hospital, and the quantum is there too, looking inside you. The great machine called an MRI scanner, which can produce astonishingly detailed images of the soft insides of a living body without a single cut, works by listening to a quantum property of the atoms in your own tissue. The particles at the hearts of your atoms have a subtle quantum feature, a kind of internal orientation, and the scanner gently nudges them with magnetism and radio waves and listens to how they respond. And from that quantum whisper, it builds a picture of the inside of you. People have their lives saved, their tumors found, their injuries mapped by a machine that reads the quantum state of their own atoms. And here is one that reaches back to the other long night we spent together, the night about space-time. The whole system that lets your phone know where it is on the surface of the Earth depends on a network of satellites, each carrying a clock of extraordinary precision, an atomic clock. And an atomic clock keeps time by counting the unbelievably steady quantum vibration of atoms, the rhythm at which they shift between two precise energy states. The very definition of the second, the basic unit of time itself, is now written in terms of this quantum tick. So when you find your way through an unfamiliar city, you are leaning on two of the deepest theories in physics at once. Einstein's relativity, bending time aboard the speeding satellites, and quantum mechanics, ticking away in the heart of every atomic clock. The two great theories, the ones that cannot be made to agree with each other at the deepest level, quietly cooperating in your pocket to tell you which way to turn. Now, let me show you the strangest everyday gift of all, because it connects directly to the weirdness at the center of the night. Remember the smeared-out particle, the one that is not in any single definite place, but spread across a range of possibilities. That spreading has a consequence so strange it sounds made up, and yet we rely on it constantly. A quantum particle can sometimes pass straight through a barrier that, by all the rules of the solid world, it should not have enough energy to cross. Because it is not a hard little pellet arriving at a wall, but a spread-out wave of possibility. A small part of that wave can leak through to the far side, and so, every so often, the particle is simply found on the other side of a wall it could never have climbed over. It did not go over. It did not smash through. It was, in a sense, on both sides at once, and sometimes it ends up on the far side. This is called quantum tunneling, and it is real, and we use it. The memory in the small drives and cards and phones that hold your photographs and your messages. The kind of memory that keeps its contents, even with the power switched off, works by deliberately pushing electrons through a thin barrier they classically could not cross, by tunneling. Every photograph you have stored, every file you have saved on such a device is held in place by electrons that tunneled through a wall. We have built our memory of our own lives on top of one of the strangest quantum effects there is. But the deepest example of tunneling is not in any device. It is in the sky. It is the reason there is a sky to look at. The reason there is warmth on your face on a clear day. The reason there is life on this world at all. Look at the sun. Its light and heat come from a furnace at its core, where the lightest atoms are crushed together and fused into slightly heavier ones, releasing energy. But there is a problem with this, one that puzzled physicists for a time. The cores of these atoms carry the same kind of electric charge, and like charges push each other away, fiercely, harder and harder, the closer they come. And it turns out that the core of the sun, hot and crushing as it is not actually hot enough. The atoms there, by the ordinary rules, do not slam together with quite enough energy to overcome that fierce repulsion and touch. By the solid world physics, the sun should not be able to burn. It should not shine. And yet it shines. It shines because of quantum tunneling. The atomic cores, spread out into waves of possibility, do not need to fully climb the wall of repulsion between them. Every so often, a small part of their waves leaks through, tunnels across that barrier, and they fuse after all. The sun burns not because its atoms have enough energy to meet, but because, now and then, they tunnel through the wall that should have kept them apart. The light that has fallen on every living thing for billions of years, the energy behind nearly every meal you have ever eaten, the warmth that makes this world a place where you can be alive to rest tonight, all of it pours out of a quantum trick. Without the strangeness we have been exploring, without particles that are spread out waves of maybe rather than hard, definite pellets, the sun itself would go dark and we would never have existed to wonder about any of it. And underneath even that, there is the quiet quantum fact that holds up all ordinary matter, including you. The reason atoms have the structure they do, the reason they stack into the rich variety of the elements rather than all collapsing into the same dull sameness, The reason matter is stable at all and takes up space and can be built into stars and stone and living bodies comes from a deep quantum rule about how the smallest particles are forbidden from crowding into the very same state. That single rule shapes the entire table of the elements, and so the whole of chemistry, and so the whole of biology, and so you, the solidity of the chair, the firmness of the floor, the fact that your hand does not pass through the blanket, is, at the very bottom, quantum. The strangeness is not somewhere far away. It is the thing you are made of, and the thing that holds you up. So this is the quiet marvel to carry down towards sleep. We have a theory we do not fully understand. We cannot agree on what it means, on what is really happening when a measurement is made, on whether the world is one or many, on how the smear of possibility becomes a single solid fact. The deepest questions about it are exactly as open tonight as they were a century ago. And yet, not understanding it has not stopped us from using it to remake the entire world. The computer and the phone, the laser and the fiber, the glowing screen and the gentle bulb, the scanner that sees inside you, the clock that tells you where you are, the memory that holds your photographs, the very shining of the sun and the solidity of the ground, all of it runs on this one strange, beautiful, unfinished idea. We built a civilization on a mystery. We use it every single day, perfectly, while still arguing about what it is. There is something almost reassuring in that, if you let it be. You do not need to understand a thing completely in order to live inside it and trust it and rest in its warmth. We have been doing exactly that with the whole quantum world for 100 years. There is one question we have circled all night without ever landing on it, and now, gently, near the end, we can. It is the question, at the very center of the theory, the one Schrodinger's cat was built to sharpen, the one that has gone unanswered for 100 years. When the smear of possibility becomes a single fact, what actually happens? Remember the shape of the puzzle. The great equation describes a wave of many possibilities flowing along, smooth and lawful and predictable. But every time we look, we find only one outcome. The many become one. And the theory, for all its power, does not tell us how or why or what counts as a look, or where the line falls between the quantum world of coexisting maybes and the ordinary world of single solid facts. This is the measurement problem, and it is not a small technical gap. It is a hole in our understanding of what is actually real. We have the most successful theory in history, and we cannot agree on what it says is happening in the world. What we have instead are interpretations, different stories told by serious physicists about what might really be going on underneath the equation. They all use the same mathematics. They all predict, as far as anyone can currently test, exactly the same experimental results. And they paint wildly, irreconcilably different pictures of reality. Let us hold 3 of them up to the light, gently, one at a time, and you will see just how far from settled this is. The first is the oldest, the one that grew out of Bohr's circle, the one usually taught first and often called the standard view. In this telling, you should simply not ask what the particle is doing between measurements. The wave of possibility is not a real physical thing out in the world. It is a description of what we know, a bookkeeping of probabilities, and when we measure, it collapses, and the collapse is just real, a basic feature of nature with no deeper mechanism beneath it. The world genuinely is indefinite until observed, genuinely does deal in chance, and there is no point asking for the hidden clockwork, because there is none. This view asks you to make your peace with the strangeness and stop demanding a more comfortable story. Many physicists, for a long time, did exactly that. But it leaves the deepest questions pointedly unanswered. It tells you to stop asking them. And to many thoughtful people, that has always felt less like an answer and more like a refusal to give one. The second story is the most staggering, and it has been gaining serious supporters for decades. It was put forward in the year 1957 by a young physicist named Hugh Everett, and it makes one bold move. It says there is no collapse. None. The wave of possibility never collapses at all. The great equation, the smooth, lawful flow of many possibilities, is the whole truth, always, with nothing added. But then, you ask, why do we only ever see one outcome? And the answer this story gives is breathtaking. We do not only see one outcome, all of the outcomes happen, every single one. When a measurement occurs, reality itself divides. The world splits into branches, one for each possible result, and they all become real, side by side, no longer able to touch one another. In one branch, the cat lives, and there is a version of you who opens the box and finds it alive. In another branch, equally real, the cat has died, and there is a version of you who finds it so. There is no randomness, because nothing is selected. There is no collapse, because nothing is lost. There is only the endless, ceaseless branching of reality into countless parallel versions, each one carrying its own copies of everything, including you. This is the many worlds idea. It is, in a strict sense, the simplest reading of the mathematics, because it just takes the equation at its word and adds nothing. And the price of that simplicity is an almost unimaginable extravagance, an endlessly multiplying ocean of parallel worlds, in which everything that can happen does, somewhere, to some version of you. We cannot tell whether it is true. It makes the same predictions as the others. But some of the sharpest minds in physics believe it is the most honest picture we have. The third story keeps the thing Einstein wanted most, a definite real world, and pays for it in the coin he found hardest. In this view, worked out in its fullest form by a physicist named David Bohm, building on an early idea of de Broglie's, the particles are real, solid things with definite positions at every instant, exactly as common sense demands. There is no smear, not really. The particle is always somewhere specific, but it is guided, carried along by a real wave that pushes it, a wave that fills all of space and feels the whole arrangement of the experiment at once, both slits every detector and steers the particle accordingly. This restores the solid, definite world. It even restores a kind of clockwork determinism, but it does so only by making that guiding wave thoroughly non-local, able to respond instantly to distant things, exactly the faster-than-light connectedness that Einstein called spooky and could not abide. So it survives the verdict of Bell and aspect, but only by embracing the very strangeness Einstein was trying to escape. It is a definite world, but not a local one. You can have your solid reality back, but the spooky action comes along with it, unavoidably. 3 stories. A world of irreducible chance and uncrossable mystery. A world endlessly splitting into countless branches. A world of definite particles steered by a ghostly, all-seeing wave. Each told by serious people. Each fully consistent with every experiment ever performed, and no way, at present, to tell which, if any, is true. This is the honest situation, and it is worth stating plainly rather than smoothing over, because the smoothing over is how people get misled. We do not know what quantum mechanics means. We know, with breathtaking precision, what it predicts. We do not know what it is telling us about reality. A century of the most brilliant work has given us a theory that works perfectly and that we still cannot interpret. The mystery the night opened with is not a loose end we tidied along the way. It is still here, exactly at the close. It is perhaps the deepest open question in all of physics. And we are not finished with this theory. We are, in a sense, just beginning to do the most ambitious thing of all with it, which is to stop merely using its strangeness and start truly harnessing it. For most of the last century, the superposition and the entanglement were things we observed, things we explained, things we built ordinary devices around. But lately we have begun trying to compute with them directly, to take the smear of possibility, the particle that is genuinely in many states at once, and use that very manyness to do calculations that no ordinary machine could do. This is the quantum computer, and it is the great frontier now. The idea is to use particles held deliberately in superposition, entangled together, so that they explore a vast number of possibilities at the same time, and to coax from that a few specific problems answered far faster than any normal computer ever could. It is enormously difficult because the delicate quantum states fall apart at the faintest disturbance, the same constant contact with the world that protects Schrodinger's cat from ever being both alive and dead. The machines that exist today are still small, still fragile, still error-prone, still feeling their way. But the direction is clear. We have spent 100 years learning that the world is, at bottom, a place of coexisting possibilities and impossible connections. Now we are learning to build with that, to make the strangeness work for us, on purpose. If it comes to its full flowering, it will be the second great gift of this theory, after the transistor, and it will have grown from exactly the features Einstein found least believable. The superposition he distrusted, the entanglement he called spooky, turned into tools, turned into machines. There is no better proof that the strange world is the real one than that we have begun to engineer with it. So let us come, at last, back to where we started, and let the night close softly around the question it opened with. We began with a paradox, a theory that has never once been wrong and that no one can fully make sense of. A theory that built the modern world, that runs in the device in your hand, in the light around you, in the sun overhead, and that tells us, when we look closely, that reality underneath is not solid and definite the way it feels, but a shifting cloud of possibility that only settles into single facts when it is observed. And we began with a man, Albert Einstein, who helped lay the first stones of this theory, won the highest prize in science for his part in it, and then spent the rest of his life insisting it could not be the final truth, who could not believe in a God who plays dice, who was certain that a saner, solider, more local world was waiting underneath, and who died still searching for it. And we found that the universe asked the question as directly as we know how to ask it, answered against him. That the spooky action is real, that there is no local hidden clockwork underneath, that on the deepest question of his later years, the greatest physicist of the modern age was, simply and provably, wrong. Not because he failed to understand the theory, but because reality turned out to be even stranger than the strangeness he was fighting. His beautiful, stubborn, wrong intuition was the very thing that showed us how to find that out. He pointed at the strangest corner of the theory and said, "Surely not this." And the universe answered, "Yes, this, exactly this." There is a kind of peace available in that, if you want it, here at the edge of sleep. It is the peace of not needing the world to be simple in order to rest in it. Einstein wanted a universe his intuition could fully hold, and he could not have one, and neither, it turns out, can we. The world is stranger than our minds were built to picture. Particles that are spread out waves of maybe a cat that is neither alive nor dead. Two things, parted across the whole width of the world, still answering as one. And underneath all of it, holding up the solid floor and the warm blanket and the ordinary evening, a layer of reality we use perfectly and understand not at all. You do not have to solve it. No one has solved it. The greatest minds of a century have left it exactly as open as they found it. And the world has gone on turning, and the sun has gone on shining by its quantum trick, and the warmth has gone on falling, all the same. So let the questions stay open tonight. The way Einstein never could quite bear to, and the way you safely can. Let the particle stay in both places. Let the cat stay in neither state. Let the wave stay uncollapsed. There is no measurement you need to make tonight, no box you need to open, no answer you are required to choose. The strangeness will keep. It has kept for 100 years, and it will keep for 100 more. Patient and unhurried, humming away beneath everything, asking nothing of you at all. The theory that runs the world, and that no one understands, will still be there in the morning. The two slits and the bands that come and go. The dice the universe rolls at its very root that Einstein could not accept, and we have learned, slowly, to live beside. The impossible connection threading silently through everything, all of it, real and proven, and waiting while you let go of the day and let the cloud of possibility carry you down and rest at last on the solid ground that is not solid at all, but holds you anyway, gently, the way it always has. Sleep well. The universe is stranger than we can picture, and it has been taking care of you the whole time. Good night.